Hello everyone. I'm Yue Song, the first author of the paper titled "The Optimal Admittance Matrix Problem in DC Networks." I'm pleased to present our paper in the following 15 minutes, and this work is done together with Professor Hill and Dr. Liu, and we are all from the University of Hong Kong. And my talk actually consists of the following 4 parts. So first, I will briefly introduce the motivation of our work and then present the formulation of the so-called optimal admittance matrix problem. Then the optimal admittance matrix obtained by the proposed optimization model has some interesting properties which will be discussed in the 3rd part. And finally, I will finish the talk with a summary. So let's begin with part 1, a recall of the OPF problem. So actually, as we know, an OPF problem essentially finds the optimal power injection given the network structure information. So the power injection adjustment can refer to generation dispatch or demand side management. So it is natural to consider the optimization problems in a complementary way to the OPF. That is to find the optimal power network structure given the power injections information. This problem has growing importance since the grid flexibility is becoming more significant thanks to the advanced power electronics and communication technology. Actually, some existing works have already made attempts along this direction, such as to incorporate continuous topological adjustment by fax devices or discrete topological adjustment by line switching. However, the search space for the optimal network structure in these works is highly limited due to the physical restrictions, including the capacity and the location of the control devices available. And these realistic settings, on one hand, make the obtained scheme practical, but on the other hand, fail to provide a full picture of the optimal network structure. In contrast, in our work, we will jump out of the practical factors and optimize the admittance matrix in a much broader matrix space. And by doing so, we can study the properties of the optimal network structure in a clearer manner. Let's go to part 2, the mathematical model of the optimal admittance matrix, or OAM for short. So we choose to explore the OAM problem in DC network as a first step because the formulation in DC networks takes simpler formulation. So the mathematical model is given below. So the input parameter is the node power injections P, and the decision variable consists of the admittance matrix Y and DC voltages vector V. The objective is to minimize the power loss, which is subjected to the following 3 classes of constraints: say power flow equation, physical limits, and possible stability constraints. And we will expand these constraints later. We note that the legacy network structure is completely forgotten in the OAM problem, which means that the connection between any 2 buses is allowed and will be optimized. So although this model is seemingly unrealistic, it will be seen later that the obtained results from this model are of interest to both power system theory and practice. So first, let's see the details of the power flow equation in the optimization model. So first of all, we introduce the admittance matrix as a function of line conductances, which is defined below. And then note that the admittance matrix is no longer a constant in the OAM problem, which is different from the OPF problem. Also, we allow any pairs of buses, say bus I and bus J, to be connected. And the corresponding line conductance Gij will be optimized in the problem. And with the admittance matrix defined, the power flow in DC network is described by the following equation. or alternatively, it can be rewritten into the following matrix form. So then let's turn to the physical limits adopted in this problem. So we mainly consider two classes of physical limits. The first one is the voltage limits, as usual, where we assume that the slack bus takes a constant voltage and the other bus voltages should be within an acceptable range. And the second class of physical limits are concerned with the line conductances. For example, this constraint regulates the line conductance to be non-negative, which is physically meaningful. And moreover, this constraint implies that the optimization is carried out under a limited budget of the total coupling resources. So otherwise, we may end up with infinitely large line conductance. So next, we turn to the stability constraints. The power system stability refers to the ability to regain a state of equilibrium under disturbances. And it should be noted that the stability concept relies on system dynamics, which is absent here. However, some stability properties can still be reflected by static parameters. So it enables us to introduce stability constraints with power flow parameters only. And in this work, we adopt the following constraint as a regulation of system stability, where the lambda 2 denotes the second smallest eigenvalue, or equivalently the algebraic connectivity of the admittance matrix. And this is due to the fact that a greater algebraic connectivity usually indicates better stability in some situations, and you can refer to the reference below as an example. Of course, other forms of stability constraint can be taken into consideration once the dynamical parameters are available. Okay, so the solution method for the proposed OAM problem is based on the successive linear programming. And given an initial feasible solution, the OAM problem will be solved by iteratively solving the linear approximation problem around the current solution. And we have also designed a convex problem that can provide a quality initial solution for the iteration used in the successive linear programming. And due to time limit, the details will be omitted here, and you can refer to our papers for them. So from the numerical experiments, we discovered two interesting rules held by the optimal admittance matrix given by the proposed optimization problem. Now let's look into them. So the first finding is called the sparsity rule, saying that the optimal admittance matrix is generally sparse. So let's take the figure below as an illustration. So this figure is a visualization of the optimal admittance matrix obtained from a 14-bus system. And it can be seen that a majority of the matrix entries are nearly zero. And to be precise, these entries are less than 10 to the power of -4, and hence their effects can be ignored. It shows that although the optimal admittance matrix numerically corresponds to a complete network, the part that actually matters has a sparse structure. And also note that such kind of sparsity is an intrinsic property held by the OAM problem, rather than a result from some intentional sparsification techniques. And the second finding, I think, which is the core finding of this paper, is called the proportionality rule. So let YII denotes the optimal self-admittance of bus I, and we plot the points showing the relationship between YII and the absolute value of PI in this figure, and where we can observe that in each of the three presented scenarios, the optimal self-admittances are nearly directly proportional to the corresponding power injection in its absolute value. It means that we can achieve a low power loss if those buses with heavier generational load have greater self-admittances. And the proportionality rule can also feed back to power system dispatch. So on one hand, this rule tells the nanostructure that best suits a certain power injection profile. On the other hand, it also indicates the direction to adjust power injections for loss reduction. That is to make the power injections more proportional to the corresponding self-admittances. So let's take the following experiment to illustrate this viewpoint. So first we have the power loss of 0.023 per unit in a randomly generated scenario for power injections. Then if we keep the total amount of loads unchanged and adjust the power injections to make it proportional to the self-admittances, then the power loss is decreased to 0.017 per unit, which is significant. So note that the above results are obtained by ignoring the stability constraint. So now let's discuss the impact of including stability constraint. We find that these two rules are still valid when adopting a moderate stability constraint. However, if the stability constraint become highly conservative, the aforementioned two rules no longer hold. And it should be pointed out that this conclusion is specific to the adopted stability constraint. Regarding the algebraic connectivity, the impact of other types of stability constraint is currently an open question. So finally, let's summarize our paper. So in this work, we propose the OAM problem that finds the optimal admittance matrix for a given power injection profile. And this problem provides a complementary viewpoint to the traditional OPF problem. Now, we find that the obtained optimal admittance matrices have two interesting properties, say the sparsity rule and the proportionality rule. And okay, here are some possible future directions to explore. First, the results needs to be extended to AC power networks to make more sense. And in addition, the engineering applications of the observed two rules needs to be further explored. So that's all, and thank you for your attention. Oh, I think you need to open your microphone.
Sorry. So I thought the microphone was not mute. Okay, can you read the questions, or do you prefer that I read for you? The panel, the question and answer panel. Can you see it?
Okay. Yeah. I saw the question.
The first
raised
one
by Daniel Moza.
Yeah. Can you read it?
Yeah. Should I read it before I answer the question?
Yeah, well, you can read it loudly, please.
Yeah. And then asked, have you tried finding the worst admittance matrix as opposed to the optimal matrix? I wonder if the worst matrix is the opposite of the optimal admittance matrix. That means opposite of the observed rows. Oh, I think you raised a very good point. But unfortunately, I have not yet tried to find the worst case in this problem. Yeah, I will try it later. I think your expectation Is correct. Is correct because from some numerical experiment that I have done, I generally I cannot say it precisely, but generally I find that we will have a greater power loss if the self admittance is less proportional to the power injection. Okay, then another guy, Nawaf Nazir, asked another question. He said that if I followed correctly, the objective in your optimization was to reduce power losses, and using this, you get a sparse solution. Did you try this problem with other objectives? If so, the sparsity results still observed. Yeah. Yes, that's yeah. Actually, I didn't try other kind of objective function in my work, because I think that is partly due to that in DC networks we don't have as as fruitful choices as what we can do in AC networks. But yeah, I will take your suggestion into consideration, and which is very important. And another anonymous one asked if can you please clarify the power loss, what power loss is in the DC network representation of power grids. The power loss in a DC network refers to the resistive loss caused by the power transfer over the power network, because in DC network we don't have line reactance, but we do have line resistance, and any current flow through the resistive lines will induce a certain amount of resistive loss, and the power loss I was referring to is the resistive loss in the DC network. And another guy,
Patrick Pansetici, please.
Patrick, yeah, Patrick asked, do you think what it could be possible to include N-1 criterion in your approach? Yes, if I include N-1 constraint, then this formulation will be generalized into the so-called, in my viewpoint, it will be generalized into the so-called security constraint OPF. And I think we would have a different picture for the optimal admittance matrix, because those matrices have to be ready for the N-1 contingency. Yes, that's a very interesting direction to be explored in the future. Yeah.